Welcome. In last class, we solved problem 11-2, and 11-2 actually we determine the hydraulic loss in clean bed filter. We are going to now do something more on hydraulics, now about backwashing hydraulics. As you remember, when we continue to do filtration, say this is filter with grain, this bed, and when we do continue filtration, after some time the contamination, the suspended solid and colloidal particles clog the filter, and then hydraulic head or head loss increase. Then we have to stop the filtration and clean that filter using backwashing. And we do backwashing by changing the direction of flow upward. So what happens during backwashing, that bed, if this is the bed, this is bed gets suspended and depth of bed increase. This is depth of expanded bed, uh, the system, and this one is the depth of bed. So if we want to place wash troughs, we must know the depth of expanded bed so that we will place the wash trough so that the crust of wash trough remain at that level, and then water overflow into the wash trough and then go out. We can use this equation to find the depth of expanded bed. This equation here, you can see the epsilon. Epsilon is bed depth porosity. D is depth of bed. F is the particle fraction retained during safe analysis, and epsilon E is the porosity of expanded bed. This is porosity of expanded bed, not bed, expanded bed. We can find the porosity of expanded bed using the equation given below. Now remember, when we do backwashing, we have to have higher velocity so that all particles of the bed get suspended. So this flow regime in this during this backwashing is kind of turbulent. So we can find this expanded bed porosity using this equation, which involve the backwash velocity, which also involves particle settling velocity and Reynolds number. The Reynolds number can be determined using particle settling velocity, diameter of particle, and viscosity. Or we can use this equation as well, where D60 is 60th percentile diameter. Either way we can use. Okay, but there is a problem. You see here, the porosity of expanded bed is related with backwash velocity, particle settling velocity, and Reynolds number power 1. So we have to find particle settling velocity to find expanded bed porosity. Then particle settling velocity we can find using this equation here, which can be determined if we know drag coefficient. The drag coefficient is a function of Reynolds number, and Reynolds number again is a function of particle settling velocity. So to find particle settling velocity, we have to use particle settling velocity, which is kind of confusing. There is a dilemma here. So what we have to do, we have to use here estimated settling velocity. Somewhere we have to use from experiment some value and then find a Reynolds number. Then we use Reynolds number to find drag coefficient, and then we use this drag coefficient to find particle settling velocity, and then particle settling velocity we can find Reynolds number and put it here to find expanded bed velocity. So we will use first particle velocity to find this Reynolds number using this graph. So in x-axis here you see particle diameter, and y-axis you see estimated settling velocity. So if you know the particle diameter, which has certain specific gravity, we can find settling velocity. And we can use our number and then we go backward. So we are going to do this in example 11-3. Let me read for you. Determine the depth of the expanded sand filter bed being designed for Ottawa Island, which is in example 11-2. So whatever data we are using, uh, we have used in 11-12 2 is valid for us. So we have filtration rate here. We have a specific gravity of sand, the shape factor, particle bed porosity, temperature is given, so we can find the viscosity and the depth of bed filters. This is here. So we will use this information in 11-C. So we are going to use some information with in the sieve analysis we obtained in 11-1. So now that bed we are using has particles of different diameters, and we want all of the particles remain in the system when we do backwashing, even the smallest one. So if we see the particle diameter, smallest particle here is there, 0.000126 meter. This particle should stay in the system. So if we see graph 0.000125 is somewhere here, and then we can find this estimated setting velocity. So backwash velocity should not be more than this one. So we select backwash velocity for these particle which has diameter of 0.000126 or 0.0126 centimeter, have a specific gravity 2.6. We can find this from figure 11-7. The terminal settling velocity 1 centimeter per second. So we can select the backwash velocity 1 centimeter per second. Should not be more than that. Similarly, as we find for this particle the estimated settling velocity, we can do for all diameter the estimated settling velocity from the figure 11-1. This, and so on. If we know this settling velocity, it means we can calculate Reynolds number. So we can calculate, for example, for this particle, we know the shape factor is 0.82, particle diameter is 0.002 meter, estimated settling velocity V is here 0.3 meter per second, and viscosity is we will get from appendix this value, and you will get this Reynolds number is given here, and you can do for this one as well as, and you find new Reynolds number and so on. So if you know all of the Reynolds number, you can use this Reynolds number in this equation here given here to find drag coefficient. Drag coefficient is 24 or R plus 3 by R half plus 0.34. We use this equation because the Reynolds number here is bigger than 1, but not that big. So it's in between laminar and turbulent. So we can find for this one 0.65 for this particle, and for other particle as well we can find all drag coefficient. So we found the drag coefficient. We can use this equation to estimate the setting velocity again. So we know drag coefficient, we know that the density of water is 1000 kg per meter cube, and then because the specific gravity of particle is 2.65, if you multiply with uh, the density of water, we can get the density of particle. So we know these two terms. We know the diameter. We have different diameter here. So let's say this diameter. The drag coefficient is known also. We just estimate it here. So we can put everything here, and we will get the estimated settling velocity here. Okay, we have these columns now filled. This is new estimates. As this is new. velocity. We just calculated, and we have this information already given because in the last example we know percentage retained during sequence analysis, and we can convert into fraction. So here we can put these things in fraction here. This is actually F. Now we know fraction retained, also we know the particle settling velocity, we know the drag coefficient. We can find again the Reynolds number using the equation, same equation is phi d v d by, which is given here. So we use this time new, this new is calculated settling velocity. The diameter is here, psi factor is 0.82, and the viscosity is already we know. So we can find new Reynolds number here for each diameter. Okay. And then because we know the Reynolds number, we can find this exponent by putting the number here. So for this number, if we put here, we'll get 0.41, and we use here 0.41 to calculate the porosity. Remember, already we have found VB is 1 centimeter per second, which is 0.01 meter per second, and we have used just estimated, calculated the particle settling velocity, that we can find expanded bed porosity for that particle is 0.255. So here is 0.255, and we can do for all diameters of the particle. Similar computation we can do. So we know this expanded bed porosity. We already know the F is here, so we can have this factor for each diameter, and then we can sum them up. But we can get this number. This is actually this part. We can put it here. Epsilon is 0.45, depth of bed is 0.5, and this whole figure is 2.53. We can find the depth of expanded bed is 0.7 meter. Now if we compare the ratio between depth of expanded bed and depth of bed, the 0.7 and 0.5, it gives 1.40. It means that if we have depth of bed 0.5 meter, we need 40% more to reach to this 0.7 meter. So if we subtract depth of bed from depth of expanded bed, we need actually from here to here 0.2 meter plus safety factor. So for example, 0.2 multiplied by safety factor 1.5 is 0.3. So we have 0.8 meter depth of expanded bed. And it is important because if we have this bed, we have to have the crust of our bathtub at 0.8 meter. Okay. I ask you to solve the example 11-4 and 11-5 from your textbook, and also read this section 11-12, 26 to 11-45. Okay.
Recording.
Schedule. I see that there are 3 dots, but I don't see any.
सर जावेद रिकॉर्ड कर रहा है.
जावेद रिकॉर्ड कर रहा है. जावेद, please send me. Okay. When you complete the recording, send me this recording. Okay.
Okay.
So you can see my this slide, huh? Yes, actually, sir. I want to show you some videos now, but not now, but after some time. So another thing is hydraulic head loss during back filtration. So because of course when you are doing back filtration, even that time when you do back filtration. Even that, then the pressure here and the pressure here will be different. So there will be head loss. So we can calculate this head loss during back washing using this equation, which is Fg is equal to mg. F is equal to mg, which is actually force is acting upon on the expanded bed. So if we subtract density of media from density of media, the density of water for the uh, fraction excluding the expanded bed porosity over the area A over the depth D, which will give us the value of mass of bed. And if you multiply with G, then we can get the force. So we can use this equation to calculate the force of gravitational force. And then if we have to get to know the head loss, we have to convert the force into pressure. So if we divide this force with the area and density and then gravitational field, we can calculate the head loss. We convert this force into pressure. So if we do this, we can have this side. So we can calculate the head loss during backwashing using this equation. Okay, let's talk about some practice of granular filtration media. We use usually filter or type of filter based on what is the influent characteristics or influent water characteristics, what is the raw water characteristic, and what will be the what are the treatment step we have taken already before the filtration. So we have to see the characteristic of raw water. Also we have to see the treatment processes that precede the and follow it. Some treatment process before filtration or what will be the treatment process after filtration. Based on these two, we can select the filter type. Usually we use depth bed anthracite monofilters, this kind of filter, because it can accumulate head loss. This kind of deep bed filter, because they are deep, then they have even at the low rate they can have certain head loss, but they accumulate the more particles. Please turn off your audio. Somebody's call is coming again and again and disturbing me. So it can because it is deep, so we can accumulate a lot of particles. It is very good when raw water is not properly conditioned. So when there is no treatment process before the filtration, then we apply the deep bed anthracite monofilters. We use dual media or multimedia filter if raw water is from large lake, because the concentration of the particles or suspended particles or colloidal particles vary too much based on season, whether it's flooding or not, rain or not. So turbidity will change during very short period of time. So we use dual media in this case, two different media. We use mono media filter when source water characteristic changing in source water characteristic with time is very much low. This concentration of contaminants are constant or very low also, because we do some chemical conditioning before this. In this case we use mono media. So we have general tendency, if we want to we can manage the head loss at low flow rate, then we use this kind of filter, mono deep bed anthracite. If raw water is not conditioned very well, we use dual or multimedia. Raw water is from large lake. If there are some treatment process before chemical conditioning and the sedimentation, then we use the mono media filter. And how many filters we use? We use minimum 2 for a small water plant, flow rate less than 8,000 meter cube per day, or 4 for larger plant, flow rate is 8,000 meter cube per day. The Kamawara is the one scientist. He gave one equation that we can use this equation to calculate the number of filters if we know the flow rate in meter cube per day. We can calculate the number of filters for that flow rate. But generally, if flow rate is less than 2, at least we use 2. If flow rate is more than 8,000 milligram meter. There are some design filtration rates also. So rapid sand filter, we usually use 7.5 meter cube per meter square hour or meter per hour. This is filtration rate. For dual media filtration rate, we can go for 15, or deep media mono media filters, we can go up to 25. So here you in this table 11-3, you can see the rapid standard sand filter for head loss 0.3, we can go up to 5 or 7.5 if we can have, or we can accommodate head loss 4.5, then 7.5 meter per hour, or 10 if we can, even 10 if we have standard dual media with the head loss with 0.3 meter, and then dual media 12.5 with the head loss 0.45, and dual media 20 if we can manage the head loss 0.6 meter, or dual media to 25 if we can handle 0.75 meter of head loss. So depending on head loss, we can select the filtration rate. This head loss is the head loss which we can manage. Means then if we have this is the water depth, this is the media, and we can manage this much in our structure because water level will increase. So if we can manage this much head loss, we can apply this filtration rate. And the area, to calculate the area of bed, we use this equation. The area of bed is equal to a maximum daily flow rate divided by a number of filters multiplied by the Q. The Q is the filtration rate. So usually up to 200 meter square for large plant, and 200 meter square, more than 200 meter up to 200 meter for very large plant, and 200 meter square for large plant, and 25 to 100 meter square for average flow. 50 meters suggested by some books, Kamawara and your water treatment principle and design, these two books. We can use this equation just to calculate the area, but we have to consider these limits. Okay, this is one of the diagram of a rapid sand filter. You can see here rapid sand filter has filter in filtration box. So in one filter, this is one filter box. You have usually two filter cell. So one filter cell and another filter cell bisected with the gullet. This is a gullet in between. So one box has two cell divided by in between gullet between these two cells, and you can see here some wash troughs. So there are some wash troughs here. And you can see deep here some filter bed. So I want to show you some video, starting from 2-minute video and some 4-minute video and little bit more longer video, but I will try to go it quick. So first let's watch this one, and please tell me if you don't see. I mean, cannot see. So you can see this video. See here, this is backwash is starting. Now backwash water is flowing into the wash troughs and into from wash trough into the gullet. This is gullet. Okay, uh, this that was one um, video. This is another video. All of you are watching this video, right?
Yes, sir. Yes, sir.
Okay, I play now another video. We have 4 minutes. So they are just removing water from the filter now before backwash. So they first withdraw or remove all of the water. So this is gullet, okay? This is gullet and this are wash trough. So water will come into gullet. See here, the water will enter into gullet and gullet. Sorry, water is withdrawn and this. So you see here, there are some air flow from the bottom to up. We call it air scouring. So they apply air, not water. So just to mix everything. Now they are doing backwashing from downward up, water is coming up. And this you see here, this is gullet here, water will go into the gullet. Sorry, in back wash trough. So from wash trough into gullet. So through wash trough, this is this gullet. So this wash trough, water is falling into gullet. And this is dirty water. You see, with time it will be cleaned. So backwash now stopped. Now influent water and the raw water is coming in. Okay, so there is another video which is a bit longer, 7 minutes. So I will go very quickly. I just want to show you some airs covering and some other thing. So I will play it, but we will I will pass or skip anything. So here now air blowing will start, or air is covering we call it. From bottom it is coming. Air is coming from bottom. For 1 2 minutes, this air is covering still. Water is coming also from down. Backwash is started. You see, water is going into wash troughs and from wash trough into gullet. See, here or here is following into gullet, falling into gullet. So it's getting clear. See, Water is getting clear. It's clear now, almost clear. So let me show some pictures also of rapid sand filter. This is a filter room. You can see many filter box in one room. This one is you see here a box and two cells. So one cell and another cell, and the water is filled above the wash trough. You see here water is above, the level is above the wash trough. So during filtration, this is during filtration, water is above the wash trough, above the gullet. Everything is submerged in the water. And this is the empty uh, box. You see here the you see here some marks here. This is the level of water during filtration. So everything is submerged. So water filter, what is one filter box has two filter cell, and then in between the filter cell there is a gullet. It is connected with the backwash trough. So backwash trough will carry the water from cell into backwash troughs, and from backwash trough into gullet, and from gullet out. You see here some concrete. This is made of concrete. So these concrete wash troughs, and these wash troughs are made of steel, backwash trough, and this wash trough are made of plastic. So there are different type of there are different type of backwash troughs. So it can be made of concrete, can be made of steel, can be made of plastic. And here you can see some wash arm. So this pipe is connected with wash arm to clean the surface of bed. There are some nozzles here, surface wash arm connected with these pipes. And you can see here model of dual media filter. So coal, graded sand, some gravels and coarse gravels placed on vertified clay filter blocks. So this is one diagram of model filter bed. The backwash has this panel, electrical panel to control it. This backwash is starting, so you can see dirty water is rising and then begin to fall into wash trough. So from wash trough it will go into gullet. You see here the backwash is started, and from wash trough it is falling into gullet. Water becoming clear, and a little bit you see here some foam also formed because of organic matter present in water. It's getting better and better, and now more clear, become clear. Sorry. So I stop here at this slide. We will start about some more practice, and then I want to